Hi everybody, this is Miss Frazita. We're looking at Chapter 1, Section 2 today, Transformations of Linear and Absolute Value Functions. So this section is, as the title suggests, very focused on just linear and absolute values, which makes it easier actually than Section 1.1 where they were hitting you over the head with all the types of transformations there are with various functions. Okay, so our goals, move this out of the way here. So our goals for today, three of them. The first one is basically the translations and reflections. The second one is the stretching and shrinking. And the third is when you start combining the transformations. You have maybe two transformations in one problem. So we'll focus on those three things today. I put at the bottom there again, just as the title suggests, we're really focused on absolute values and lines both. Okay. A couple words, maybe just to make you think about these translations and transformations a little bit differently. We're talking about whether they're rigid or not. So a rigid transformation is any of them that basically preserve both the size and the shape of the original function. So for example, if you take a function, let's say a parabola, if you want to think about that, and you simply take the parabola and add 3 to the end of the equation. That's going to make the parabola shift up by 3. Or you subtract 3 from the end of the equation and it moves it down by 3. So the parabola itself has changed its location in space, but it hasn't really changed its size or its shape. So that we would say is an example of a rigid transformation. Okay, so basically these are going to be the ones that shift the graph either up or down or right or left. Now reflections are also in this category where you're flipping it over the x-axis or flipping it over the y-axis. Again, the size and the shape doesn't change, you're just simply looking at the mirror image of it. So the non-rigid transformations then are those that are stretching and shrinking it. So it's basically changing the slope of the curve as it moves along. So it will be a different shape then, we would say. And you could stretch or shrink it in both the vertical direction or the horizontal direction. Of course, if you're stretching it in the vertical, oftentimes that looks like you're squishing it in the horizontal. So it gets kind of confusing depending on how you write the equation, which way you want to think about it. Okay, a couple examples. First one, let's look at a linear example, meaning a line. So our equation f of x is 4x minus 9. So just thinking of a line in the form y equals mx plus b, or slope is 4, down 9. So part A, write a function g whose graph is a translation 5 units up from the graph of f. So this time f is considered our starting point. Instead of just thinking our parent graph of a line is y equals x, we're going to start with this function f of x being 4x minus 9, and we want to move that 5 units up. So I know that if I just add a number to the end of the equation, that affects it by shifting it up by that amount. So my g of x equation will be whatever f of x is and adding 5 to that equation. Okay, so in other words, we're altering the output of this. So my f of x function, I plug in 4x minus 9 plus 5, and I get 4x minus 4 when I simplify. Part B, write a function h whose graph is a translation 1 unit to the right of the graph of f. Okay, so I know that if I want to shift my graph right or left, then I have to replace the x in the equation with an x plus something or x minus something. So this problem is asking me to move 1 unit to the right. So that's going to be replacing x with x minus 1. So my h of x equation will be f of x minus 1. So what is f of x minus 1? Remember your function notation. I go to the f function, replace x with x minus 1. So I have 4 times x minus 1 minus 9. Simplify that and you get your answer. Let's move on to look at an absolute value problem and practice with doing some reflections. So here's our function at the top, example 2, f of x is absolute value of x minus 5 and then minus 4. So again, already if you're thinking of the parent graph of just y equals absolute value of x, you should be thinking of a V shape where the point part of the V, the vertex, is sitting at the origin. And then you would, for this problem f of x, you would need to shift it to the right by 5 and shift it down by 4. So our f of x function is a V shape where the vertex has the coordinates 5 minus 4. So part A, they ask you, write the function h whose graph is a reflection in the x-axis over the graph of f. Okay, so when I want to flip it over the x-axis, I'm going to be putting a minus sign out in front of the equation. So, that vertex, instead of having the coordinates 5 minus 4, I want it to be 5 plus 4. So, and then I want it to be opening down instead of up when I reflect it. So if you visually thinking about what this should look like, it would be a V shape that's upside down where the vertex was 5, 4. Okay, but algebraically, basically what we're doing is we're throwing a minus sign out in front of the entire equation. Okay, the entire equation is what y is, so really you could think of it as putting a minus sign in front of y, and that will flip it over the x-axis. So the negative out in front of the whole thing, I distributed in, and I got my answer. Part B, write a function g whose graph is a reflection in the y-axis of the graph of f. So I want to be flipping it over the x-axis. So instead of having some point where I go over to the right and down, I'm going to go to the left and down. So the x value is really needing to be reversed. So replacing x with negative x is going to flip it over the y-axis. So here I have g of x is f of negative x. So again, now I'm altering the input instead of the output. It's the x value that I'm putting minus sign in front of instead of the previous part where I was putting a minus sign in front of the y, if you think of f of x as y. Okay, so replacing x with negative x in the equation, I went ahead and did that. And then just to simplify it, since you have negative x minus 5, both of those negatives could be factored out in front. And because it's in absolute values, that negative sign actually will get ignored anyway, because we're taking the positive of x plus 5. Okay, so final answer there at the bottom. Let's do a little with stretching and shrinking. We'll stick with the absolute value idea. So f of x starting out with absolute value of x minus 1 and then plus 2. So again, for this particular problem, if you're thinking of your V shape, it would move it right 1 and up 2. So you'd have a V opening up with its vertex at 1, 2. So part A, write a function g whose graph is a horizontal stretch of the graph of f by a factor of 5. Okay, so whenever you're trying to affect the graph horizontally, then it's the input, the x value, that you're going to have to alter. And now anytime it is a horizontal effect, everything is kind of reversed from what most people feel like it should be. So if you're trying to stretch it by a factor of 5, instead of multiplying x by 5, we actually multiply it by the reciprocal of 5 to get it to stretch. And again, if you plot some points, you'll see why this is the case. So f of 1/5 x, if I go to my equation, replace x with 1/5 x, you'll see how I got my answer there. Part B, write a function h whose graph is a vertical shrink of the graph of f by a factor of 0.25. Now again, the vertical is not backwards from what you think. Anything that affects it vertically is just the way you would clearly understand it to be, at least for most of us. So if I'm trying to shrink it, I need to multiply by a number smaller than 1. So here we're shrinking it by a factor of 1/4, or 0.25. So my h of x equation will be 1/4, or 0.25, of f of x. So again, the vertical effect is when you have the number out in front of f. That means that you're altering the output rather than the input. So it's not that I'm multiplying just the variable x, I'm actually multiplying the entire equation, which is y, or f of x. And I left my answer pretty much like that. I guess I distributed the 0.25 times 2, or 1/4 of 2, right, it's a half. Combinations of transformations basically just means they're going to ask you to do more than one thing to your function to get a new function. So here we're starting off with just our parent graph of a line, f of x equals x. And it says to let the graph of h be a horizontal stretch by a factor of 8, followed by a translation 10 units down. Okay, so h of x is going to equal, and then we want the horizontal stretch. So horizontal is basically affecting the x, right, the input. So we want it to stretch by a factor of 8. Well, we're going to multiply by a number smaller than 1 to stretch it. Remember, anytime it's horizontal, it's backwards from what kind of makes sense. So stretching factor of 8 means a 1/8 multiplying by the x. And followed by a translation of 10 units down. So now, oh, I want 10 units down. I put a plus 10. It should be a minus 10. Sorry. Make sure you correct that. This should be a minus sign, 10 should be a minus 10, not a plus 10 on the end. Okay, and that would be it. So again, the number on the end is the vertical shift up or down. It should be minus 10 to go down. Next example, combinations of transformations. So describe the graph of g of x as compared to the graph of the parent graph, f of x. Okay, so if we're starting with just our parent graph of absolute value of x, what did I do to it to get this g of x function? So I see three numbers in there, a 1/2, a minus 2, and a plus 3. Okay, so the minus 2 that's inside the absolute value brackets there, anytime you're altering the x or replacing x with x minus 2, that's going to be shifting it horizontally. And in this case, because it's minus 2, it goes to the right. Again, kind of backwards from what you think because it's a horizontal effect. Minus 2, you might think, goes left. Left seems like a negative direction. But no, a minus 2 goes right. Okay, the other two numbers are affecting it vertically. So the 1/2 that's out in front is a vertical effect. You're multiplying it by half, which means the y-coordinates are all cut in half. So it's a vertical shrink by a factor of a half. And the plus 3 on the end is shifting the graph up by 3. So again, you start off with your parent graph of the V shape. You move it to the right by 2. You shrink it vertically by a factor of a half. And then you shift the whole thing up by 3. So here I have a total of 6 problems for you guys to try. So basically I'm giving you your functions f of x, and over on the right I'm going to have you translate the graph and reflect it and then stretch or shrink it, okay? So your goal is not to graph it unless you feel like it, but your goal is to write out what the new equation g of x would be. So you can write g of x equals something in terms of f of x, and then you're going to translate that to the actual equation, what f of x is. Okay, so I would suggest go ahead and pause for a moment and try those 6 problems when you're ready. There is one more slide with the answers. So you can fast forward when you're ready. Okay, so let's move on. Here are the answers. So number 1, we were shifting it up 5. You can see the answer. Number 2, we're shifting it down 3. Number 3, let's see, looks like you were flipping it over the x-axis. Number 4, flipping it over the y-axis. Number 5, the horizontal stretch, factor of 2. And number 6, a vertical compression or shrink by a factor of a third. So if you have questions on these, let me know in class when I see you, or tutorial. Thanks.